The last video I'm going to make today is about conformations in cycloalkanes. So these are cyclic, meaning they're in rings. So cycloalkanes have the general formula C to the N, H to the 2N. Right? So these are just alkanes that are in rings. We use the cyclo prefix to denote that they are rings. And so we have to talk about what's called angle strain. So if you think back to general chem, right? Tetrahedral carbon has 109.5 degree angles. In cyclopropane, to get those three carbons to be in a triangle shape, we have to really condense those angles. Okay, so it gets condensed significantly to force it into a three-membered ring. Okay, so this is a non-linear overlap. So they get compressed to 60 degrees as opposed to 109.5 degrees. All right, so this is not ideal. This is not ideal. We call that a bent bond. So when you look at cyclopropane, there's a significant amount of torsional strain here because of condensing those bond length angles so much. You have to do that though if you're going to have these three tetrahedral carbons be in a three-membered ring. When we get to cyclobutane, you're going to have the same thing. Okay, this is the bond angle you would expect based on the tetrahedral carbon. What you get is a 90-degree angle. And so if you're looking down the Newman projection, right, these hydrogens are eclipsing each other. And so there's ring strain here from both the angle strain and then the torsional strain from the eclipsing. Okay, so again, there's a lot of ring strain in cyclobutane. So cyclobutane has a way of relieving that. It's to become non-planar. So in other words, it's not flat. It actually is bent. It's kind of folded looking. Right? So if we do this, make it look this shape, right? Now those are not right on top of each other, fully eclipsed. And so it's kind of like a, I think your book calls it an envelope shape, right? To decrease that torsional strain and also to remove some of that eclipsing crashing. When we get to cyclopentane, you're going to see the same thing, right? So if we're looking straight up this bond right here, we're getting some eclipsing, and then this relieves a lot of that tension, okay? And so again, it's kind of that envelope shape, and beyond here, we're not going to have any more flat, right? And until we start talking about things that have double bonds in them, that's a whole different story. So when we get into cyclohexane, which is a six-membered ring, there are two conformations that we have available to us. We have what's called the chair conformation. So it looks kind of like this figure from your book, person sitting in a chair. Right? So there's the chair conformation. Alrighty. And then we have the boat conformation. So it looks kind of like a boat, right? So these appear on the top. The chair conformation is the more favored of the two, okay? Because there are no eclipsings. Let's go back and look at the picture. See, there's no eclipsing. Whereas in the boat, there is eclipsing, okay? So this is why we say the chair is more favored and the bond angles are better in the chair conformation. Now there is an option in between the chair and the boat. It's called the twist boat. All right, and so here's the picture, energy diagram showing that. Here's the chair, here's the chair, here's the boat, and here's the half chair. And now we need to talk about, this is something that's going to be a big part of this chapter, is drawing these conformations and identifying axial and equatorial positions. Right, so axial ones, these are represented in red, are all sticking straight up. Okay, they're vertically parallel. Whereas equatorial are directed outward. I remember when I was in organic for the very first time, this was something that I really had to just break out my model kit to see. I had a hard time visualizing it. I had to get out a model kit and look at it. So if that's something that's helpful for you, definitely want to take advantage of model kits. And so when we convert between the chair and the boat, okay, that's something that you're going to need to be able to do. And the important thing to remember here is that any substituent that's axial now is equatorial in the new position. Okay, so just make sure that when you're doing your conformational shifts, right, you're going to switch whatever's axial to equatorial. So this is a really just quick and dirty vocab review. It is not meant to replace working the problems and all that kind of good stuff. But I hope that this helps you